In this video, we're going to take another look at how we can examine the assumptions of a linear model. So remember that a linear model distills a relationship down to just a few numbers. Even if you have millions and millions of points of data, you can attempt to summarize the relationship between those variables down to just a few points. But obviously, we make certain assumptions about the relationships of the data to be able to do that. And if those assumptions are wrong, then the results of our linear model might be wrong or misleading. So as we've seen in a multiple linear regression, we often find ourselves in a situation where we can't plot all of the original variables in a graph, just because the graph would have more dimensions than we can visualize. But we can still examine the model's assumptions using visualization by creating different types of graphs. To do that, we will need the residuals of the model, as well as the observed values of the response variable, by which we mean the actual values. And we'll also need the predicted values of the response variable. You can see these three quantities illustrated here in this two-dimensional graph. The observed values, right, are the y values, the response values of the original data points, right? So the red points, where these points truly fall on the y-axis. Whereas the predicted response values are the y values of the blue points, i.e., if we were to take the same value of the explanatory variable on x-axis and look at where the linear model blue line is predicting the point should fall, that is the predicted value of the response variable. We also have the difference between those two numbers, illustrated by these vertical gray lines here, which is the residual, right? The difference between the observed and predicted values of the response variable. We can calculate the predicted values and the residuals using two functions, add predictions and add residuals, which are part of the model R package. Each of these functions takes a data frame as the first argument and a model as the second argument. And so we can write code like you see here, where we start with the data frame we use to create the model, we pipe it to one of the functions and write in the model as the second argument, and then pipe it onto the next function, again writing in the model as the second argument. The output will be a data frame, which we can then assign to a new variable, like you see here, df_augmented. This data frame will contain new columns, a column called pred and a column called resid, which are added by the add predictions and add residuals functions respectively. And as you can see here, right, we have the original response variable, which for this first row of data, right, was 51.5. And we also have now the predicted value of the response variable, which in this case is 58.25. And we have the residual, which is the difference between those two numbers. So the first assumption of the linear model, and the most important assumption of the linear model, is that there is actually a linear relationship between the response variable and the explanatory variables. By a linear relationship, we mean that there is no curvature, no systematic curvature to that relationship. To determine this in a multiple linear regression, what we can do is plot the observed values of the response variable versus the predicted values of the response variable. Using code like you see here, and this will always be a two-dimensional graph because we'll always only have one response variable, right? And so we'll only have one column of observed values and one column of predicted values. What we want to see is that there is a linear relationship between these two variables. And to help us determine that, we can plot a reference line using the geom AB line function like you see here. And this reference line should have a slope of 1 and an intercept of 0. Because if there is a linear relationship, then we should see that the predicted values and the observed values are relatively similar, right? So they should fall along a line with a slope of 1 that goes exactly through the origin. To help us further, we can add a trend line using the geom smooth function, and this will show not a linear model, but kind of a curved trend line through the center of the data in different parts of the graph. And what we ideally want to see is that this more or less follows the linear trend line in black, like you can see in this example here. The second assumption is that the variance of the residuals is constant. And to examine this assumption, we can create another two-dimensional graph in which we plot the residuals on the y-axis versus the predicted values of the response variable on the x-axis. In this case, we are going to have a reference line that is a horizontal line, a flat line, at y equals 0, which we're adding here with the geom h-line function. What we want to see is that the spread of the residuals is constant throughout this graph, and that it's not narrow in one part of the graph and wider in another part of the graph. Again, to help us, we can add a trend line with the geom smooth function, and what we want to see, as in this example here, is that the trend line more or less overlies the linear reference line created by the geom h-line function. The third assumption that we care about is that the residuals have a distribution that is close to a normal distribution. If you recall, a normal distribution was a particular type of unimodal symmetric distribution. And one of the easiest ways to determine this is to create a type of graph called a quantile-quantile plot, or a QQ plot for short. We can do this with functions that come with the ggplot2 package, geom underscore QQ and geom underscore QQ line to create the reference line. And in this case, the aesthetic mapping is from the residual column to an argument called sample. And what these functions do is they plot the actual residuals versus the theoretical distribution of the residuals if they were to be in a normal distribution. And so what we should see is that if they do have a normalish distribution, then they should fall more or less on the black reference line, as in this example. If you see that the points don't really fall on this line, maybe they cross it in one or two places, but the rest of the points are not on the line, then that would indicate that there are significant deviations from the normal distribution.